The most powerful ship that humanity has built was not born at sea. It was born in a foundry. Before a single plane took off from its deck, before its nuclear reactors generated their first watt, someone had to cut the first piece of steel. Someone had to design it. Someone had to manufacture it, block by block, for 11 years. This is that story. The year is 2001. The United States Navy has a problem it can no longer ignore. Its Nimitz-class aircraft carriers have been in service for decades, and the cost of maintaining them is rising without end. The technology inside those ships is decades old. Steam catapults from the last century. Systems designed when floppy disks were cutting-edge technology. But the real problem is not the technology. It is that to operate a Nimitz, 6,000 sailors are needed, and at that scale, the human cost becomes unsustainable. Each sailor represents a salary, a bunk, a meal, and a life managed by the state. Multiply that by 6,000 across a fleet, and the numbers threaten to sink the budget before the ship even leaves the pier. The Navy needs a ship that does more with fewer people. They need a vessel that operates with the efficiency of a modern automated factory rather than a manpower-intensive relic of the Cold War. In Newport News, Virginia, the largest shipyard in the Western Hemisphere receives the call. They are asked to design the aircraft carrier of the 21st century. Not an improved version of the Nimitz, something completely new. A ship that wouldn't just carry planes, but would redefine the projection of national power. The engineering team starts with a blank sheet of paper. This is a rare moment in military history. Usually, you iterate. You take what works and you tweak it. Not this time. And the first thing they do is not draw a ship. It is to ask themselves a single question. What is the bottleneck in an aircraft carrier? The answer arrives quickly. It is not the size. It is not the power. It is the speed with which you can launch and recover aircraft. An aircraft carrier is a factory. Its product is aerial sorties. If you make more sorties per day with less personnel, you win the war before firing a shot. The deck of a carrier is the most dangerous 4.5 acres on Earth. It is a chaotic ballet of jet fuel, high-tension wires, and screaming engines. To fix the bottleneck, they had to reinvent the dance. With that clear, the engineers designed everything around a single idea: more combat tempo, fewer bottlenecks, less personnel. The steam catapults disappear from the design. These were massive, complex systems of pipes and valves that required constant maintenance in fresh water. The mechanical elevators disappear too. They replaced them with electromagnetic technologies that do not yet exist. We are talking about taking the technology of a railgun and applying it to a 30-ton fighter jet. In paper, the Ford is revolutionary. It features a redesigned island, the command tower, which is smaller and moved further aft to create more space on the deck for pit-stop-style refueling and rearming. In the practice, it is a $13 billion ship built with unproven technologies. It is a gamble of historic proportions. If the magnets don't fire, the ship is just a very expensive floating hotel. That will have consequences, but first, you have to build it. The USS Gerald R. Ford is made of steel, not the steel of a construction beam, high-strength naval steel, an alloy known as HSLA-115, a special alloy designed to withstand explosions, water pressure, extreme heat, and decades of operation in the mark. It is designed to flex without breaking, to endure the corrosive salt of the Atlantic and the Pacific, and to protect the nuclear core buried in its belly. There are more than 100,000 tons of it in the ship. To put it into perspective, the Eiffel Tower weighs 7,300 tons. The Ford is 14 Eiffel Towers of specialized steel. That steel arrives at the shipyard in huge plates, some as thick as the palm of your hand. The first machines to touch them are the cutters. Lasers and plasma torches trim each plate with millimeter precision, following the digital blueprints of the ship. These are not just drawings. They are a 3D digital environment where every nut and bolt is accounted for before the first spark is struck. The cut pieces are bent with giant hydraulic presses, curves of the hull, angles of internal compartments. Every curve is a calculated defense against the physics of the ocean. Then comes the welding. Cientos de soldadores trabajan simultáneamente uniendo esas piezas en estructuras cada vez más grandes. The shipyard smells of burnt metal 24 hours a day. The sparks do not go out. The electric arcs do not rest. From the freezing winters of Virginia to the humid, suffocating summers, the work continues. And each weld is inspected with ultrasound and X-rays. Because a faulty weld in an aircraft carrier in the ocean is not a manufacturing error, it is a death sentence. When you have a nuclear reactor and thousands of lives on board, there is no acceptable margin for error. The integrity of the hull is the only thing standing between the crew and the crushing depths of the sea. But an aircraft carrier is not built from the bottom up as a building is built. It is built in separate pieces called blocks. The Ford is divided into more than 500 structural blocks. Each one is a complete section of the ship. Some are the size of a room, others are monstrous, the size of a 4-story building. And each block is built in parallel, de forma independiente. While the bow is being built, the stern is being built. While the engine room is being assembled, the control island is being raised. This is no accident. This is the miracle of modular construction. This method allows workers to access the interior of the ship while it's still open to the sky. It allows for the installation of massive components that would never fit through a door or a hatch. Construir en paralelo reduce los años de trabajo a la mitad. Inside each block, the systems that belong to it are installed before joining it to the rest of the ship. Tuberías, cables eléctricos, conductos de ventilación. Everything has to be in place before the assembly. Imagine the complexity: 14 million feet of electrical cable. Enough to stretch from Washington, D.C. to California and back. 4 million feet of pipe. All of it must align perfectly when the blocks meet, because once that block is joined to the others, reaching its entrails is almost impossible. In the peak of construction, more than 5,000 shipyard workers work on the Ford in a single day. They are the hidden army. Engineers, master welders, electricians, and painters. The shipyard works in 3 shifts. The Ford nunca descansa. It is a living, breathing organism of industrial might, growing in the heart of Virginia. The finished blocks weigh between 100 and 900 tons. To move them and join them, you have to use the largest cranes in North America. Newport News has 2 giant gantry cranes. The largest, nicknamed Big Blue, can lift 900 tons, the equivalent of 150 elephants, and move them with the delicacy of a watchmaker. When a block is ready, the crane lifts it from the shop and carries it to the dry dock where the ship is born. The dry dock is a concrete pool without water, excavated in land. It measures more than 660 meters long. There, the blocks are lowered one by one with precision of millimeters. Each block must fit perfectly with the previous one. The tolerances are less than a centimeter in structures of 900 tons. It is a feat of geometry. When the block is in its exact position, thousands of welders return to work, and the ship grows, bloque por bloque, mes tras mes, año tras año. The silhouette of the Ford begins to dominate the skyline. It becomes a landmark. But for years, it is a hollow giant, a steel shell waiting for its heart and its brain. On November 9, 2013, something occurs in Newport News that no one who witnessed it will ever forget. The dry dock begins to flood. The gates open. The water enters slowly, then with more force. This is the moment of truth for the shipbuilders. The huge steel hull, which has been resting on concrete blocks for years, begins to float. For the first time in its existence, the USS Gerald R. Ford is a ship. It has no active reactors. It has no flight systems. It does not have most of its equipment, but it floats. And in the shipyard, the thousands of workers who built it applaud. That day, Susan Ford Bales, daughter of President Gerald Ford, breaks the bottle of champagne against the hull. A new weapon has been born. But still, the majority of the work is missing. Launching a ship is just the beginning of its life. Now, they have to make it breathe. After the launch, the systems must be installed. The 2 A-1B nuclear reactors are installed in the depths of the ship. These are a massive leap forward. They are smaller, simpler, and produce 3 times the electrical power of the previous generation. Each one produces 700 megawatts of thermal energy. They do not manufacture them in the shipyard. They arrive assembled, shrouded in secrecy. Introducing them into the hull requires crane maneuvers that engineers practice for weeks before executing them. With this power, the Ford could provide electricity to a small city for 20 years without ever refueling. Then comes EMALS, the electromagnetic aircraft launch system. Cuatro vías de 90 metros, kilometers of electrical coils under the flight deck. The power electronics that make possible 120 megawatts in an instant. Unlike steam, EMALS can be tuned. It can launch a heavy bomber or a light, fragile drone with the same precision. It is the smart catapult. After, the 11 electromagnetic weapons elevators. This will be the system that causes the most problems. In a Nimitz, elevators used cables and pulleys. In the Ford, they use linear motors. The shafts that run through the ship from the magazines to the flight deck have to be aligned with minimum tolerances. In construction, those tolerances are not met. The steel of a ship this size actually bends and shifts as it settles. The shafts did not align. The doors would not close. The engineers correct, rebuild, and recalibrate. The program falls behind schedule. The costs rise. The critics, and there were many, ask if this ship can really work. They call it a floating paperweight. They say it is too complex for the real world. The answer would come in the tests. On April 8, 2017, the USS Gerald R. Ford goes out to the ocean for the first time. These are the sea trials. The reactors are put to full power. The propulsion systems push the 100,000-ton hull to more than 30 knots. The water of the Atlantic smashes against the bow. The vibration of the engines hums through the steel. On deck, the EMALS technicians launch test planes for the first time. The system works. After years of doubts, the most powerful electromagnetic motor installed in a warship launches a combat aircraft into the Atlantic sky. The acceleration is smooth, silent, and terrifyingly fast. The weapons elevators continue giving problems. Only 2 of 11 work during the first tests. It is a PR nightmare and a technical puzzle. Pero los ingenieros no abandonan. Each failure is documented, analyzed, corrected. Elevator by elevator. It is a war of attrition against engineering glitches. 6 functioning in mid-2020, 9 in early 2021. The 11th certified in December 2021. The paperweight was finally becoming a weapon. On May 31, 2017, at Norfolk Naval Station in Virginia, the commissioning ceremony of the USS Gerald R. Ford is held. The Secretary of the Navy signs the documents. The sailors run aboard in formation, manning the rails in their white uniforms. The United States flag goes up the mast. From that moment, the Ford is an active warship. It cost $13 billion. It took 11 years to build. It employed more than 5,000 people at its peak. It used more than 100,000 tons of specialized steel. It is a monument to American industrial will. But a ship isn't a ship until it goes to war. In October 2022, the Ford deployed for the first time to the Mediterranean, not as a test, as a real operation. With its carrier strike group of 10 escort ships, it entered the Mediterranean in a moment of maximum geopolitical tension. Its presence was a message written in steel. On deck, the planes take off with EMALS every 45 seconds. The pilots land on the AAG, the Advanced Arresting Gear, which is also electromagnetic. From 280 kilometers per hour to 0 in 2 seconds. No more violent jerks from hydraulic pistons. Now, software controls the tension of the wire to catch the plane perfectly every time. During the 2023 deployment, the crew moved 78 tons of ammunition through those 11 elevators without a single major problem. The system that almost destroyed the program worked exactly as promised. It allowed the ship to move bombs and missiles from the deep magazines to the jets faster than any ship in history. More than 22,000 successful launches and recoveries since the ship entered service. Each one a testament to the thousands of people who touched that steel. Everything started with a steel plate in a shop in Virginia, with a welder applying his electric arc to a joint that would eventually form the keel of the most powerful ship in the world. with an engineer looking at a screen and wondering if something so ambitious could really work. The Gerald R. Ford didn't just meet the challenge, it set a new standard for what a nation can achieve when it refuses to build the safe option and chooses instead to build the future.